What is a partition of a set? A set P is a partition of a set X when the following conditions hold. Firstly, every element A of P must be a non-empty set. Secondly, for every element X in X, there must exist a unique element of P, a unique element, let's say A of P, such that X is an element of A. Notice that this quantifier here with the exclamation mark is there to say that not only A exists for every X, but there is only one such A, that X is an element of A. There is also a third condition. Every element of P must be a subset of X. We could combine conditions 1 and 3 into one condition by saying that A must not be empty, and at the same time it must be a subset of X. But what is a partition of X intuitively? Well, intuitively, P is a partition of X when P divides X into disjoint blocks. For example, consider a set X consisting of 5 elements, 1, 2, 3, 4, and 5. A partition P of X would organize these elements into groupings, into blocks. For instance, 1 and 2 could go in the same block, 4 and 5 could go in the same block, and 5 could be a block of its own. In terms of the previous formal definition, this picture would be encoded as a set whose elements are the blocks, which we view as subsets of X. The first block over here would be a set that only has 2 elements, 1 and 2. The second block would have 3 and 4, and the third one will be a set having just one element, 5. Notice that by the definition of a partition, an empty block is not allowed. We can't have empty set being an element of P. Neither it is allowed for there to be a block that overlaps with other blocks. For example, we cannot have a separate block containing 4 and 5 because it would overlap with the others. This is because of the second condition defining a partition, where we stated that every element of X must belong to exactly one element of P. In this case, if we had another additional block 4, 5, the element 4 of X would belong to 2 blocks, one of them being the block consisting of 3 and 4, and the other one being the block consisting of 4 and 5, which would then violate the condition. So the blocks cannot overlap. Neither can there be elements that are left out of being inserted in any of the blocks. X cannot have an element 6, which does not belong to any of the blocks. If it did, then such P would no longer be a partition of X. Why? Because for the element 6, there must exist a unique element of P that contains 6. Well, in this case, there does not exist any. You can have several different partitions of the same set. The one shown here is just one of them. In the case of the set X, having 1, 2, 3, 4, and 5 as its elements, we could have another partition that groups these elements in a different way. For example, a partition that puts 1 and 3 in the same block and 2, 4, and 5 in the same block as well, but different from the first one. Notice that the elements of a partition are these in the case of the second partition and these in the case of the first one. So the elements of a partition themselves are not elements of X, they are rather subsets of X. The elements of those elements are the elements of X, which is what it means that they are subsets of X. The concept of an equivalence relation is closely linked with the concept of a partition. When you have a set X in which certain elements are similar to each other, such similarity relation, which will be an equivalence relation, naturally partitions the X into similarity or equivalence classes. The partition obtained this way is called the partition obtained from a given equivalence relation. If the equivalence relation in this case were E, then the corresponding partition would be written as follows: X over E. The symbol here represents the idea of division. We're dividing X by similarity classes. For an individual element of X, let's say this one, the small x over here, the block inside which X can be found is written as this. You put square brackets around your object and the name of the equivalence relation as a subscript. Notice that if I picked another element from the same grouping, let's say x prime, this would yield the same value for the so-called equivalence class, because x and x prime belong to the same class since they are similar. The partition in this case, which as we said is written X over E, would be the set of all such possible blocks, which can be parametrized by the individual representatives of each block. So let's say X, Y, and Z. So the partition in this case would be the equivalence class of X, the equivalence class of Y, and the equivalence class of Z. In fact, any partition can always be obtained from an equivalence relation. Take a partition of, let's say, another set Y, which groups elements into blocks, as that is what a partition does. Now we can define an equivalence relation by declaring xy to be in the relation when x and y belong to the same group, such as here, for instance. How can we write this? Well, belonging to the same group means that there exists a block in the partition such that both x and y are its elements. This defines an equivalence relation that of course depends on the partition we started with, it is actually not difficult to check that the relation E defined by this equivalence will be reflexive, symmetric, and transitive. Thus, for any set X, we can consider all possible partitions of X and all possible equivalence relations on X. These two collections of structure, partitions and equivalence relations, are so closely related to each other that we can get one from the other by the processes described earlier in such a way that these processes are actually inverse processes to each other. For example, if I start with an equivalence relation E and I consider the corresponding partition, and then I take that partition and build from it an equivalence relation, let me call this E prime X over E, I will in fact get the same equivalence relation that I started with. Similarly, if I start with a partition P, build an equivalence relation from it, and then create a partition out of it, I will end up with exactly the same partition that I started with. Conceptually, this means that partitions and equivalence relations are equivalent concepts. They are basically different way of encoding the same information, the information of which objects are similar to each other. In the case of an equivalence relation, we encode them by ordered pairs of declaring all possible pairs of similar objects. In the case of partitions, we encode the same idea by forming groups of similar objects.